Greetings, in this video I'll talk about how to calculate the force between 2-point charges in vacuum. So let's say my first charge is Q1 and it is equal to 10 nanocoulombs and charge number 2 is equal to 8 nanocoulombs, and these two charges are, let's say, 0.05 meters apart from each other. And what the equation states is that the force between these two charges will be equal to the Coulomb's constant times, this is in free space. By the way, there's more complicated details in other cases, but I'm talking about vacuum without air, free space. This constant, Coulomb's constant, the value of which I will state in a second, times Q1 times Q2 over the distance between them squared. So this is the equation all I need in order to calculate the force between these two charges when they are let's say they're both plus, and the distance between them is 0.05 meters in space. So I can plug in these values, where the Coulomb's constant K, which is the multiplicative constant right here and it's required, is 9 times 10 to the 9, so I can put it right here. And then the rest is simply Q1, Q2. And Q1 is 10 nanocoulombs, and nanocoulomb is 10 to the 9, is a coulomb but divided by 10 to the 9. So 10 nanocoulombs is equivalent, so this is the K constant, then this will be the Q1, that is 10, and I will not use the units, I will just plug in the numbers, and I know that the result, because it's force, it will indeed be in newtons. So after all this will be the unit newtons, and I don't have to write the units of all the other things on the way. So this constant, this Coulomb constant in front, I can put it up on the fraction. So that's 9 times 10 to the 9. All right, according to this, it's approximately that. It's more closely 8.99, and it's even more closely some other more concrete number. But a way of running it, there's far more concrete ways of running it. But the simpler, nicely rememberable way is just 9 times 10 to the 9. So that's the K. Q1 is 10 times 10 to the minus 9. Coulombs, which I'm not putting there because I'm leaving out the units except for the final unit of the result, which I know will be newtons because this is force that I'm looking for. Then the second charge is 8 times, again, 10 to the minus 9 times 10 to the minus 9 is because it's nanocoulombs. Alright? And then it's over r squared. R is 0.05 meters, also denotable as 5 times 0.01 to the second power, or in other words, 5 times 10 to the minus 2. But I have to square it because in the denominator it's squared. So 5 times 10 to the minus 2 is the same like 0.05 meters. By the way, meters is the unit, is the SI unit that is plugged in straight into this equation, just like coulombs is the unit that is plugged into this equation, into this formula. So now I can just rewrite all of this. 10 to the 9 will cancel, for example, with this one. Then I can connect all these numbers that are not 10. By the way, I can delete this initial formula. This is basically the pattern that we are following here. So that is the most important part, and now I'm just basically doing an example of it. So basically what's left here is 9 times 8, which is 72. And then 10 times 10 to the minus 9, that's 10 to the minus 8. And then because there is 10 to the minus 2 to the second power, I can rewrite this once again, maybe. So the top side is this, and this, that's alright. That has been taken care of because these two have been cancelled out. Then 9 times 10 times, that's 10 to the minus 8, and yeah, times the 8. Alright, so the top side is taken care of. And the bottom side, I can rewrite it to this new step, which will be 5 to the second power times 10 to the minus 4 power. Alright. And again, the result is going to be in newtons. Alright. So right now, I'm almost at the finish. This 72, it's also writable as 7.2 times 10 to the minus 7 as follows, because I can take away 10 divided by 10 and then multiply by 10 to the first power. and then in the denominator is 5 squared times 10 to the minus 4, and the 10 to the minus 4 can be taken up as 10 to the 4. 10 to the minus 4 in the denominator is like 10 to the 4 in the numerator. These two things together give 10 to the minus 3, and the result is something like this: 7.2 over 25 times 10 to the minus 3 newtons, of course. This is the result, alright? Of course, this number, you can put it into the calculator and get a decimal approximation of the result of it, but I'm not doing it now. This is approximately the result of, this is actually still the exact result considering the numbers that I used in the beginning. If I said that the column constant is exactly 9 times 10 to the 9, then of course this result is the exact result, and once the decimal approximation is gotten through a calculator, then that will be an approximation. But so far this is the result, and this is basically it's something around 0.3, something between 0.3 and 0.4 times 10 to the minus 3 newtons is the force between these 2 point charges.